it. Okay, I think we're not recorded. Here, this is the articles in which that was published. Material this was by former student. That was part of his diploma thesis. And that I don't know where it's here now. And here in the first paper, it was done for three-dimensional spaces. In the third one, for four-dimensional. I will also speak about four-dimensional spaces because the Davis-Stewart equation does have physical meaning.
Even four-dimensional Dirac operator.
No, two-dimensional. But surfaces in four dimensions. Yes, that's relation. I start with just with recording what is the Darboux transformation. Probably people do know that, but what is it? This is just the basic of this stuff because that's the quite popular transformation in the one-dimensional Schrödinger operator with potential u. This one, and we have the solution of the zero energy level, so that H omega equals 0. Here we can put E omega and then move E, the constant E to the left-hand side because this is an analytical thing. It doesn't relate to any functional spaces. We are not specialized that U has to be fast decayed and so on. This is just roughly speaking. And the Darboux transformation is defined by the solution and maps H into another operator. And solutions of this equation H psi equal to psi for all E. It maps into solutions of the new equation related to the new potential. So if we know, for instance, if the operator H is solvable, then we can easily construct another solvable operator starting with this one. This is the story. Every solution, how it's done? Every solution to this equation defines a factorization of the operator H in the product of two operators of the first order. A top formula joint operator A at A. This is A is minus dx plus V. This is a top dx plus V, and this logarithmic derivative formula. Then there are two transformations, just swapping of these two portions, nothing else. So if psi is the solution of the equation, is the formal eigenfunction of the operator H with the eigenvalue E, then psi tilde is easily one can check is the eigenfunction of the new operator with the same eigenvalue. Algebraically, it looks like P squared minus U prime. This is UT. So we replace the potential U by this potential. P squared minus U prime, is derivative. This is called the factorization method. First good application of this method was the solvability of the harmonic oscillator in the previous book by Dirac, the principles of quantum mechanics. So let us reconsider the case, then the Darboux transformation results in shifting by the potential by the constant. So then I have to write down that U is V squared plus V prime. And util is V squared minus V prime. So this is just we extract from the previous potential V prime multiplied by 2. What is this? Then this is a shift is by the constant. It means if only V prime is a constant. Assume that it's A, it's positive. And then D is equal to AX. Then if it's logarithmic derivative of some eigenfunction, then the operator has to be the operator of harmonic oscillator. Nothing else. It follows from this commutation relation, and this commutation relation is just Darboux transformation. Nothing else. Written down that if H psi equal E psi and H A psi it's equal E plus A psi. So this is how it's called creation and annihilation operators in quantum mechanics. So NA tilde is the annihilation operator. So we decrease the eigenvalue of psi by A, by the constant A. Apply the operator equal. And now what's the next? We notice that 2e minus a, the square root of chi, is non-negative. So this implies that e has to be greater or equal to a over 2. Assume that we have some e and we start to apply an annihilation operator going down with eigenvalues. If we go, if at one moment e doesn't equal to a over 2, we go below this level. And that's impossible due to this inequality. So at one moment it stops at a over 2. So then the annihilation operator acts on this eigenfunction, and this eigenfunction has to lie in the kernel of annihilation operator. So it's solution of this equation, x plus ax psi equals 0. And this is the solution, this equation. This is the ground state of this operator with the eigenvalue a over 2. And then we start to apply the creation operators going up. So all eigenfunctions is the form a in some power this n minus y applied to psi 1 with eigenvalues. This is eigenvalues form of the arithmetic progression. So this is the simplest derivation of the eigenvalues and eigenfunctions of the harmonic slate. That is very important in physics because there's just a whole quantum electrodynamics is based on this so on. First, it appeared actually in this book by Dirac, not in the first edition, but in the fourth or the fifth one in the beginning of the 30s, because the first years this book was republished every year. So every year there was a revised edition. But later I had known that actually what Dirac did, he used this derivation, which is actually due to Fock. In this you can see the relation to Fock spaces, multiplication by z and so this is just the Fock spaces. So this is actually due to Fock. And in the beginning of 40s, Schrödinger noticed that that actually this trick just related to the factorization. And then in 1950, there appeared an article by Infeld and Hall, in which they used this method for constructing new solvable models. Actually, Schrödinger also did that. Constructed some solvable operators, and they were published in 40s in the Proceedings of Royal Academy of Ireland. This time Schrödinger was there, so it's quite complicated to find these articles. And then these Dirac operators appeared in different forms in many other articles. For instance, adding the new point to discrete spectrum for one-dimensional Schrödinger operator is also be written down as the replication of some Dirac or some Dirac transformation. But originally there was the Moutard transformation. The Moutard transformation appeared as a reduction of the Moutard transformation, and Moutard was specialist in geometry, in projective differential geometry. And it is as follows: let a two-dimensional potential Schrödinger operator, H omega minus Laplace per E. Their Laplace is the two-dimensional Laplace operator, and the Moutard transformation is defined as follows. So from this operator we construct another one minus Laplace per E. We are subtracting the double Laplace logarithm omega and obtain a new potential. If psi satisfies this psi equals 0, then the function that defined by this system satisfies this new equation. So it acts only on the zero energy level, but zero energy level, for instance, if we started with u equals 0, just harmonic functions, then it's a degenerated because it's analytical stuff, it's all on the it acts on all harmonic functions. Originally, the Moutard transformation was applied to hyperbolic equation. In projective differential geometry, it was called Moutard equation. And the idea of Moutard, one of the main applications, was to construct an example of a hyperbolic plane immersed into three-dimensional Euclidean space. So there was many attempts. So locally we can immerse it, but then we started to extend it globally for the whole plane. There appeared singularities. It appears that these singularities are unavoidable because at the beginning of the 20th century, Hilbert proved the famous theorem that a hyperbolic plane cannot be immersed into half-free. So there is no such an immersion such that the first fundamental form is exactly the hyperbolic plane for constant negative curvature. But this is again also algebraic stuff, and we can easily replace it by Z. You see, the Moutard transformation describes deformations only of eigenfunction with zero eigenvalue. Direction of the Moutard transformation is multi-valued. It's defined model of multiples 1 over omega. That's due to this equation, to this product. And if you equal x and omega equal fx exponent kappa y, the Moutard transformation reduces the Dirac transformation defined by L. So actually, the Dirac transformation was derived 6 years after the time. So that's the point. The Dirac transformation became quite popular in solitary theory in the beginning of 70s. Then it appeared that we can extend it to Dirac transformation of solutions to KdV equation, because the Schrödinger operator comes into LFR of the quadratic difference equation. Quadratic difference equation, yes. So we can have a solution of the KdV equation and apply Dirac transformation at every moment of time, but it needs to add some analytical addition on top. And then you will get another solution of KdV equation. That was found by physicists at the beginning of 70s. And in their article, this transformation was called the Beckett transformation from KdV. This is exactly the rule. At every moment of the time, it's a Dirac transformation. And now, we used with Tsarevsky, we started to apply the Moutard transformation for two-dimensional Schrödinger operator to obtain, for instance, blown up solutions of the Novikov-Veselov equation and some interesting examples of two-dimensional Schrödinger operators with discrete spectrum on the zero level. And now I would like to show how this, what is the analog of this transformation to two-dimensional Dirac operators and how this transformation can be explained in very simple geometrical terms. I consider these two operators, this again normally conjoint. This is the units potential complex value on the equal unit bar. This is just derivatives in Z and Z bar. And we consider the H-valued functions of the form H is quaternions, because if psi1 and psi2 are complex numbers, this is the general form of quaternions. So the multiplication of matrices of this form is just the algebra of quaternions. It's very simple realization. So if psi, this is the vector function meets this equation, if psi equals 0, and this is the first column of this matrix, then if we substitute in this equation the second column of the same matrix, that would be again the solution, and so we may write this together as the psi equals 0. This is for simplicity because of algebraic, it's simply to work with the quaternion valued matrices. And what is the Moutard type transformation for the Dirac operator? Here is the formula quite large. So that's, we have two H-valued functions, C and P, which corresponds to, and to them we correspond to one form with values in quaternions again. So this is this one form. Minus equal 2, P top, this is just position. Sigma 3 is one of the Pauli matrices, psi plus psi z minus, and so on. This is written down. If psi and phi satisfy these two equations, Dirac equations, then this forms omega phi psi and omega psi phi are closed. And there is a defined an h-valued function is closed. Here gamma is another part of the matrices multiplied by pi. So this is these formulas. And then they put also this matrix valued function, which depends on pi psi of this form. So there is some combination and which divide it in omega bar a minus a bar minus a omega. That would be important matrix, no other computation. And now they have the theorem jointly with Moutard. If psi naught and p naught meets this Dirac equation, then for every pair of solutions of the same equations, we can construct new solutions of the equations for Dirac operators with another potential. U tilde equal U plus V. Plus W. Sorry. There's W defined by so this is we are extending these solutions of we are constructing new solutions from other ones. For U equal U bar, such a transformation was defined in articles by mathematicians from China, along Yu, Liu, and Wang. In article, it was called the Moutard transformation from the economical digital equation, published in some physical journal. But I did rewrite it in the original article, which I mentioned on the second page. In 2015, I rewrite it in these steps because it was transformed and rewritten in terms to see the relation to surface theory. Because it was quite clear that it has to have a geometrical meaning because these Dirac operators are related to surfaces in R3. So it was rewritten, some terms are remained, swapped, and so on, and now it has this form. What is this form? There is been a representation of surfaces. Originally, there was an article by Konopelchenko. There he proved this result. So we have these two solutions, Dirac equation, then these formulas define the surface in our form. That's it. So it's called then this procedure is inducing surfaces, solid on surfaces in our form. So we have the solution, we can induce a new surface. And since this Dirac operator comes into LAP triples for some solid equations. This is LAP triples. Then we can for D with the U with the real valued potential, that would be the modified numerical equation. And for general case, that would be Davis-Sturgeon equation, second Davis-Sturgeon equation, when we can construct the solid and deformations of these induced surfaces. What is this? We have the surface. If this equation reduces to some solid equation, equal also on this sub-quantity, then this eigenfunction satisfied, as in the case of KDV, linear equation of psi, so we can get the equation for psi, and then since psi and phi define the surface, we do have the deformation of surface. That was the idea, solid on deformations of surfaces.
What means solid deformation? Just how it is distinguished among all other deformations?
Solid on deformation, because first the surface is written through this representation, and psi is deformed via these linear systems, which are common to the LAB triple for some solid equation.
Why do you want to consider such? So from the point of view of surfaces in for dimensions,
Yes.
is a function of two variables in the surface. So those surfaces you like, how they are distinguished among others.
Because this equation is integral of the system, so I can write down explicit solutions. That's the only case. I can do any deformation inside.
It means that it has many families, some kind of.
Yeah, it's a KDB, it's integral system. So we can write down, so of course we can do any deformation. Deforming psi. But because you see, the A depends on potential U. Yes? And we have to know the evolution of U if we would like to deform these things. But you see, that would be very nice. And first of all, I would like to say that this construction is very general. Yes.
I heard that people sometimes say there should be representation in the context of minimal surfaces in R3.
If U equals 0, that means that psi and phi are holomorphic functions. One of them is holomorphic, another is anti-holomorphic. That would be minimal surface. So this is generalization of representation of minimal surfaces. For U equals 0, this is exactly the minimal surface. Now I explain how it's very easily to show that every surface is represented in this form. On every surface, you can take a conformal parameter. This notion was introduced by Gauss, and he proved the existence of conformal parameters for analytic surfaces, and that was proved in a very general situation. So that means conformal parameter. This is induced metric. D squared takes this form. Du squared plus d squared. This is the Euclidean metric, and it's conformal to the Euclidean metric. It's very hard. So what does this mean? Then you're writing the first fundamental form is reduced to this one. It means that the square root of dx over u is equal to the square root of dx over d, and also that these two vectors are orthogonal. That's the conformality condition. Yes. Let's write down this is in terms of dx. X is the over dz. What is dz? It's just Cauchy Riemann operator. So this is a linear combination of du. This means dx over du minus u over dv divided by 2. This means that it's written in this form. So this is are equal to each other. This 0, it means that this squares equal 0. So if we have the coordinates k1, 2, 3, 4, so the squares of the derivatives of the coordinates with respect to conformal parameter, the sum of their squares is equal to 0. And this is equivalent to conformality parameter. Now, what is this quadrant? Gn tilde n over 2 is the quadrant. Qn in Cpn minus 1. What is this quadrant? For the surface with conformal parameter z, every surface in IM, we define the Gauss map z is mapped to this to the vector, to this vector. Qn. And the image of the Gauss map has to lie on this quadrant. And actually, this quadrant is nothing else as the Grassmannian of two-dimensional oriented place in Rn. Because the Grassmannian is the oriented plane is defined by two vectors, orthogonal vectors. This is dx over du, dx over dv. We can rotate these vectors. And we can expand these vectors. So this is a du over dx and du over dv has to be taken as a homogeneous coordinates. Because multiplication of this image of Gauss map by some complex number just means that we rotate this basis and we delete this basis, nothing else. So this is exactly, so these quadrics are just Grassmannians of two planes in Rn. But in two cases, then n equal 3 and n equal 4, these quadrics are very simple. For n equal 3, that would be S2. clearly. For n equal 4, this would be the product of two of these projective lines. This is just written down how it's done. This is so-called graded. This is the holomorphic equivalence. So now take this A1, A2, and B1, A2 as the homogeneous coordinates of two focusers. P1. Write down phi is the A1, A2 bar, psi B1, B2 bar, and you will get these phi and psi. So they actually these phi and psi, they define the quadratic forms of these phi and psi, they define the Gauss map of the surface at this point, the image of the Gauss map. They define the tangent plane. So actually what gives this, and then if you know the Gauss map, dx over dz, this is exactly this one. If you substitute them here and you integrate this, you will get a surface. So this Gauss map defines the surfaces up to translation. This is translation. So this is the very general, every phi and psi reconstructed supersurface up to gauge transformation, and every surface is a global representation. Why it's called spinor? Because the surfaces of high genus, phi and psi, they're not vector functions, they're sections of some spinor functions over the surface. So we have to take the surface, take the spinor bundle, have to define this Dirac operator which acts on the spinor bundle, and globally we have it 0, and we have the representation of the surface. And for n greater than 4, the quadratics have no such rational parameterization. So this rational parameterization, a nice picture, is valid only in 2 dimensions. The surface is in upper and surface is in upper. And now let us write down, let us rewrite these equations in this form. So this is exactly, you will have here quaternion. So we can get quaternions as the action of the value of this function as belongs to quaternions if we identify quaternions with alpha. So now this formula, so it appeared in the article by the long view, one and Leo, but being written, this matrix S appears, coincides with this representation, spinor representations of surfaces and upper. They actually did it for free. So for free, I did it in the first of articles. Now I'm speaking about upper, that would be the same. And what is this Moutard transformation, which now we define here? We have matrix S. Where is the chalk? Here. We have matrix S. It gives you a surface. There is conformal parameter Z. And for surface, we can take, since S is a matrix, we take this minus 1. That's actually the Möbius transformation in that form. Möbius transformation in that form, inversion, can be written as a inversion of this matrix S. Since Möbius transformation is conformal, Z induces another conformal parameter Z on the new surface. So if we have S and conformal parameter Z, the surface, we can get it spinor representation. There is potential U, this spinor representation. Yes? And then we get the transformation. There is another surface, conformal parameter Z, there has to be spinor representation with another potential. And actually, this Bernoulli transformation from one Dirac operator to another one is just the Möbius transformation of the surface. Analytically, I can return back. It's written quite heavily. But then if you look, what is it? When it's very simple. It's the nervous transform of the surface. So to the surface we correspond, the surface with fixed conformal parameter, we correspond its spinor representation, then we get the Dirac operator. For this spinor representation, when we get nervous transformation of the surface, we get another Dirac operator, and then we do the transformation. What is now the focus in Davis-Stewart's second equation? It's this one. Let's see. I do it here. I'm very fast.
But you got more, half an hour more.
Yeah, I know. Okay. I'm used to such a task in English, yes, so it's very fast. Now, what is this? Davis-Stewart's equation. It appears in the beginning of 70s in hydrodynamics, not in solid physics. The discovery that this equation fits into the solid theory was done 10 years later. That it's a difference that's modified from the conventional equation does have physical meaning. Yeah, it's this equation. U equal I, the second derivative is C plus second derivative C bar plus this term. And there is the constraint. This is usual constraint of the two-dimensional solid equation. This potential has to be related to U as with bar equal to square root of U over C. It is actually the compatibility condition for this system. If psi equals 0, there is this Dirac operator. If psi equal A psi. That's it. Here the operator A. And also it can be written as a compatibility condition for another system in terms of the formula adjoint operator TP. When we solve the potentials U and U bar on the diagonal, this is dv phi equals 0 and phi equals AB phi with certain operator. It's a very similar one I just skipped to. So this is the so-called Davis-Stewart's second equation. Focusing, there is another focusing equation. What is this now related to this deformation of surfaces? What's the idea of making a picture? So he just defined the induction of the surfaces and their solid deformation. So as I mentioned before, phi and psi, they define the Gauss method of the surface. So they define the surface after translation. So assume now that we do have the surface, and it is induced by some phi and psi. And let me have the solution of this Davis-Stewart's equation. When we can substitute phi and psi in this linear system, construct the solution of these linear problems and get the soliton deformation of this surface. That's it. Actually, they give deformation of the Gauss maps and it defines the deformations after translation, which depend on T, because at every moment in time we can get translations in the. And there's also such deformation also depends on the resultant constraint, because it has many resolutions. Now, what I showed this in 2006, that one can define such a deformation globally, and such that this quantity is preserved. So this is the Wilmer function of the surface. The Wilmer function of the surface, it's preserved. But okay, that's globally on Torre. In Torre. Yes, I have to say on Torre because at this point it is fine side solution of spin equation that's quite complicated to work with them on living surfaces. So for Torre, that's preserved. And and this last article which I did after Moutard myself, there are some other computation that the Moutard transformation for these operators is extended to transformation of solutions to Daly Stewart's two equations. So we extended to the solutions. What are the additional terms of this transformation? Probably that's interesting. You see, this is phi. Here, this is a quantity dz. Here, this is some quantity multiplied by dz bar. Here, this could be the third quantity c times dt. So if we'd like to extend it, we have to extend it in terms of omega. So there has to be alpha. Is the that is the bar plus gamma tt. We know alpha and beta. We have to find gamma. So that's usual trick for extending this transformation for solitons. What is it? How we have defined this? D has to be a closed form. So in particular, the dt minus the gamma by the z has to be 0, and similar for this one. How is alpha transformed by dt? Alpha just quadratic of phi psi, and phi psi are solutions of this linear problem. So you will get some equation. This is the alpha for dt. Again, it's phi psi. You have to take this phi psi, substitute the derivatives in t, take this linear problem, this one. So you actually u satisfies Daly Stewart's equation, take one long term, and then it has to be derivative in z for some function gamma, for some matrix valued function. It has to be gamma. So this is a quite long computation, actually. But they're straightforward. Only the bulk and more. And I'm skipping them because just probably it's not very interesting to write down this picture. Lights. And now, what is interesting? We can start with a very simple case. Which solutions of the Daly Stewart's equations do we know? Because we have started with the exact solution. The simplest way is to take the trivial solution. E u equals 0. Yes? Nothing there. That's minimal surface. Yes? Then psi and phi are holomorphic vector functions, with one of them is holomorphic and other anti-holomorphic. It depends on so here d equals 0, u equals 0, but there are still these two terms, derivatives in this. So if we take holomorphic functions, phi psi, phi holomorphic, phi 1 holomorphic, phi 2 anti-holomorphic, then the action of A on this vector is not 0. So we still have some transformation. The potential is trivial, but we now transforming the functions in the kernel of this operation, of Dirac operator, with the same potential. There's still something. And actually it gives you some non-trivial solution. What is it? Let's be f a function which is holomorphic in Z and satisfies this equation. This is exactly this one. Psi t equal to a psi or for u equals 0. It defines the deformation of the minimal surface into equal phi C1. I'm skipping these long computations, but since we are starting with minimal surfaces, we have to find the simplest minimal surfaces in our form. That was the problem. And the special class of these solutions was found at the beginning, about 100 years ago. Even they did have some special name of the person who invented them. I found actually a big article in Annals of Mathematics by Eisenhardt 100 years ago about such surfaces and their special properties. So it's the following: if f is a holomorphic function on C, and Z1 and Z2 are complex coordinates in C2, linear coordinates, then the graph of this holomorphic function Z2 Z1 is a minimal surface in R. Now there is a quantity, as I was told by geometers, superminimal surfaces. And the simple example of superminimal surfaces are this surface they studied only for surfaces in the for space. And what is it? Since f is non-trivial, we are deforming the graph. This is deformation of this graph. So at every moment we do have minimal surface. This one, now the graph is deformed due to this equation. And at every time we're writing down the potential. U, it's U. This for generic holomorphic have written this information. V equal to I A over Z. Now in the four-dimensional case, this term A from this matrix is also becoming important. In three-dimensional case, we can do that. It's not important. So, and for every holomorphic function f, which satisfies this equation, function f, holomorphic in Z and also in T, smooth function. Then this is a solution of the Davis-Stearns equation. It's a very simple solution. When we can consider iteration of these solutions, what's this? We can construct this deformation. We can actually, since this Moutard transformation transpose another eigenfunction also to eigenfunctions, then we construct another eigenfunctions, can construct another surface and get iterations. We can repeat a lot of iterations, and we can get more complicated solutions, probably, but it's a lot of computations. I didn't do that, I stopped at the first step. At this formula. Now, what is the quantity? Simple example, then f is quadratic. F is quadratic. Then for t, which doesn't equal c, quadratic.
Sorry, I want to understand what you're saying. In the previous page, in this page, right?
Yeah,
You can see the graph defined by f.
yeah.
And they require it to be a minimal surface.
Yeah, it's always minimal surface.
Yeah, it's a minimal surface.
Yes,
But then deform.
deformed graph, yes,
Deform graph.
yes.
And the PS equation is integral equation for this.
Whoa, sorry. I have to erase your address. Yes, I'm avoiding to do that, but now let's say, no, I will erase, I should put it down, yes.
You have a family of seconds, right?
Yes. Yeah. I have a graph, it's minimal. I'm deforming it.
Yes.
It's again minimal. U is equal to 0.
So how to get this?
Okay. At every moment, I'm doing this Moutard transformation. And getting the surface, which is not minimal. Because the inversion of the minimal surface is not minimal. It has no trivial potential U. And the formula of Moutard transformation gives you new solutions of Davis-Stearns. So from the trivial solution of Davis-Stearns equation, I construct new solutions. So actually here has to be UT. Just to fit with the previous notation. This is the transformation of the zero potential. Define the different minimal surfaces. So you have the such dynamics. That's it. And what is interesting?
Sorry, I have a additional question. So f is a function of two variables.
Yes.
So for fz1, you mean for any fixed t. Yeah, and fz1 means fz1 comma t.
Yeah.
Any fixed t.
Yeah, of course. Sorry. Yes. See, it has to be holomorphic in Z and smooth in T. So if we have holomorphic, so this is just simple formula. You have any holomorphic function in Z and smooth in T, you write down the solution that there is to this equation. And now you know the geometry of this transformation, and now you can look for its singularities, for the blowing up of the solutions. And they are very trivial. Assume they have the surface. This is our point. We have the surface. Minimal. Which doesn't go through the origin. So at every moment is inverted to another surface. So that's another surface. Here the potential ut. But this surface is the default. Yes, maybe in T, yes? At one moment, it passes through the origin. And by the Laplace inversion, origin is back to infinity. And we do get a singularity at this moment, at this point. Because the potential U is not defined. So they moved in the surface, at every moment it's fine, for this potential is smooth, and it passes through infinity, and then it goes through infinity, through origin, and now we're again smooth solutions. Actually, then people are trying to improve the regularity of the Cauchy problem for solitary equations. It's usually said that what is important that this quantity is L2 normal. The potential is the first integral. So there is it's bounded. But what happens here? For C equal real, this is the general solution. At the moment that T equals C, this is 0. And the point z equals 0 is also mapped to 0. So this is just, we are going to the origin mapped to infinity. And there is also psi, the corresponding eigenfunctions of this Dirac operator is this one. What happens with the potential? Just for one moment, it's kind of shifted by a constant. So for T doesn't equal to C, the integral will functional, some multiple has to be. Depends of the invitation, because usually the fourth space, there are different normalizations for the functional. That's the square norm of U, integral square norm of U. It's equal to pi for almost all the time. But then it passes through the origin, it drops to pi. And then it regains a bit, then it became regular again. And it's again equal to pi. What happens else? You know, that's what can I say about the Laplace representation? Usually it was said that this linear problem shows that the eigenfunctions are just default. Then the spectrum is preserved, and the spectrum of this operator gives you a lot of first interval conservation of this equation. Here, what happens here? We have the sign which is the eigenfunction. It lies in the on the zero energy level, and the moment of this this critical moment C. It gains singularity here. So the spectrum is not preserved. Because when you are saying that the spectrum is preserved, it means that the evolution is well defined and there is no blow up of the solution. But here we do get a blow up, and also at this moment, this point at the zero level spectrum disappears. Just for one moment. And then the spectrum regains this eigenfunction. This point, the zero level spectrum. So I think that's related to each other. So for this equation, the blowing up of this kind and this disappearance of point at the zero level, that's a spectrum are just related. Actually, then I gave a talk once to actually in Sirius, the Soliton conference last year. I gave a talk via Zoom. So it's another guy via Zoom from another potential asked a question and they did something query. It appears later that happens also for the DB equation when U potential U is complex valued. But for the DB equation, the potential U is complex valued. But in this case, for the DB equation, the first integral is The first integral. Yeah. The first integral is integral of u squared. And this complex value, if you complex value, it doesn't have the minimum energy. But here in our case, the Google function is a real value. So this is the simplest example of blow up. And also, here it's necessary that C belongs to R. If the slightly default this constant C in because this constant from the polynomial for F, polynomial of second order C squared plus something plus C, it makes it not purely real valued, then there is no such singularity. So it means that such singularities are unstable with respect to perturbation of the initial derivatives. And what is the kind of this singularity? I have written down it for simplicity in this case. For another example, is then the F is the polynomial of the in C of the fourth degree. This is the solution of this equation. This is polynomial. Here you will get more complicated quantity. For initial time here, so by varying the powers of this polynomial, you can achieve polynomial decay at infinity, which you would like. So now it's decayed quite faster at infinity, so that's not a restriction, but I cannot achieve exponential decay by this method. It becomes singular for Ct equal to 12t squared, and it has these singularities. So the singularities are the form of indeterminacies. So it's defined everywhere except this point, but the limits of the solution along the rays which are coming in different direction to the origin are different. So this is why the polar coordinate on the complex plane. So this is just indeterminate. Now again, the first integral is equal for 4 pi, then the solution is not singular, and it drops by pi, then it's singular. Why it is this integral is always multiple of pi? Because there is a theorem that the Möbius transformation of minimal surfaces is a Willis. So now we have, in our case, we have Wilmer plane, well, minimal plane. Then we take the inversion, we get sphere, but with branch point at infinity. Infinity would be low, the points at infinity would be correspond to this branch point. And at points at infinity goes to the branch point. And now what is it? So these surfaces are related to the values of the normal function of Wilmer spheres, and they are quantized. First, they did it for modified numerical slope equations in R4, but modified numerical slope doesn't have a physical meaning to now. Yes, but for that there is tools, so you can construct this type of singularities with such drops of the first integral and a very simple geometrical meaning of these blow-ups. And now, what was known before what this famous Azawa solution was found 30 years ago, and there is even numerical experiments that it looks that all stable singularities of this devastator locally behaves as Azawa solution. It's as follows: U is initial data, and then so it decays polynomially second order, so it belongs to N2. Then for this singular moment of time.
So what's the definition of S inverse?
What?
S inverse, the inverse surface.
Which surface?
The previous page. S, the surface, S inverse. S minus 1.
S minus 1?
Yeah.
Ah. This is, we take this Weierstrass representation, we write down its representation as the matrix. So we identify R4 with quaternions. Quaternions are just matrices of this. 2 times 2 matrices with complex entries. This one, these are just quaternions, presentation of quaternions. And then we get S minus 1 for this matrix. Nothing else. And we'll do another surface. So 1 point of R4 is left to another point in R4.
So actually, you represented by the two,
Yeah.
2 by 4.
Yeah. Yes. R4 is represented by this 2 by 2 matrices. Quaternions. And then this is this Moutard transformation is just and that is the solution. Here I have to remove integral, sorry. So because this is very interesting solution, because for this special singular time, this norm modulus u squared dx dy is mapped tends to the Dirac distribution multiplied by 2 pi and the center at the origin, and then the solution regains singularity just after this moment. So this is again 1 point singularity at 1 moment of time, but completely different. And you see that the integral of u is the same, it's preserved, so it's doesn't it probably cannot be constructed by this meaning of the surface theory. So this is another solution which was known before it, but it's very interesting, and there are some numerical experiments that this is the every stable with respect to small perturbation of the initial data solution, blown up solution of Dennis-Hewson equation had to have it's similar to this dimension. Yes, but for other cases, for other singularities which are not stable, definitely, then C would be again not imperially real. That again, it's never vanishes. Then we do have these solutions with indeterminacy in these drops of the first integral. So that's one application. Probably this Moutard transformation for Dirac operators may have other applications, but now I just mentioned this one because they look quite funny. Thank you very much for your attention.
Any questions? There were many questions during the talk, but that's the speaker. Okay.
I thought that this Neutrality equation has tau function.
There is still some.
Yes.
Yeah, I think so. It has to have. It's usually in the whole quality system. But for logical decimal, what's the tau function? Target. So what are these tau functions? No, there. It was, yes. It has to be here also, yes. But I do not know.
So I just guess if there is the tau function, then usually this type of solution, the tau function could be even have simpler form. The tau function of this.
Yeah, it's okay, it's nice. It would be correspond to some cell and some Grassmannian, yeah.
Yes.
Yeah, some infinite dimensional Grassmannian, you can define which cell correspond to this type of solution. Probably, but you see, but here there were some more computations for solution this for finding for extending this, because it was clear geometrically it can be extended and quite clear geometrically what it has to be, but just to see all this analytical data right now, it was quite long. And here probably in your case it's result, probably the computation would the result would be simpler, computations would be longer. So there would be conservation law, simplicity of the answer and complexity of computations.
Okay, there are no more questions. Let us thank the speaker again. 20 minutes.